It is a region around a charged body in which any test charge is placed experiences force. Any test charge is placed within the region of any charge, it will experiences force. So we have already studied that if this is the charge and if we will put a test charge over here, Q naught, it is a test charge. This test charge experiences force. So where this test charge will go? Like this. It will move in this direction. Test charge is always plus, like this. So this Q naught will move in this direction. If you will put Q naught over here, this Q naught will move like this, along this line. If you will put over here, the charge Q naught will move in this direction. So what is the direction of motion of a test charge? It always moves away from the charge plus Q, like this also, like this also, here also, here also. So this Q naught will move away from the charge plus Q. And remember, this complete system is in the 3 dimension. For example, this is the plus Q, then the charge can move like this also, it moves like here, it moves like this also, like here, means this region is, the area is a 3-dimensional region. So this complete region is 3 dimension, and for representing the electric field we have drawn these lines. So these lines are called electric lines of forces, which are used to represent the electric field. If suppose instead of plus Q, if it is minus Q, then what will happen? If it is minus Q, then what will happen? This is a test charge Q naught. Then this Q naught will not move away due to the opposite sign. This will move like this. If you will put the test charge over here, it moves like this. It moves like this. Like this. So what does that mean? The electric lines of forces, which are imaginary lines to represent the electric field, if it is plus charge, then these lines of forces moves away from the charge. If it is negative charge, then the Q naught, the test charge, will move towards the charge minus Q. So these are the electric lines of forces which are used to represent the electric field intensity. Electric field lines are the straight or the curved imaginary lines to represent electric field. First of all, these are the imaginary lines used to represent the electric field. And second thing, the tangent at any point gives the direction of electric field. At any point, if the lines are curved, draw the tangent, and the direction of the tangent gives the direction of electric field. So we have seen the electric field lines due to the positive charge, due to the negative charge. Now we will see the electric field lines due to the combination of 2 charges. For example, this is plus Q and this is also plus Q. 2 charges having same magnitude, but they are separated by a certain distance and polarity is also same. So you have seen that if the plus charge is there, electric field lines moves away from the charge. So now see, these lines, electric field lines moves away from the charge like this, like this. Electric field lines moves away here like this. It moves away from the charge. Now these electric field lines move like this. This electric field lines move like this, and there will be repulsion between the electric field lines and moves like this. In the same way, if this is the electric field line over here, this is the electric field lines from here, then this moves like this. They will feel the repulsive force between the two charges. Secondly, if two different charges are there, for example, this is a positive charge and this is negative charge. If two different charges are there, you know, for the positive charge, the electric lines of forces, they are moving away from the charge. For the negative charge, the electric lines moves towards the charge like this. These are the electric lines by the positive charge, and these lines will move towards the negative charge like this. This electric line will go like this and it move towards the negative charge. It moves like this, it move towards the negative charge. Here, if this is the electric line, then they comes over here like this. For this electric line, it moves like this. So these are the electric lines for the two different charges. Next thing, if electric lines are parallel to each other, for example, if these are the electric lines and these electric lines are parallel to each other, this shows that the electric field is uniform. For the uniform electric field, this represents uniform electric field. Now we will study about the properties of electric field lines. First, electric field line starts from positive charge and ends at negative charge. You just studied in the previous article, the electric lines originates from the positive charge and ends at the negative charge. Second, electric field lines are imaginary lines because it gives basically the path on which the test charge either moves away from the charge or it moves towards the charge. So these electric field lines are imaginary lines. Third, the tangent at any point gives the direction of the electric field. Tangent at any point means what? Suppose this is positive charge, this is negative charge, this is the electric field line. These are the electric field lines, okay? Now, if you want to find out the electric direction of if you will put a test charge over here at the point P, then draw the direction, or you can say draw the tangent first. This tangent gives the direction of the test charge. So the tangent at any point gives the direction of electric field. That is, this is the direction of the electric field at the point P. Fourth point, the number of electric field lines passing through per unit area perpendicularly is called magnetic field intensity at that point. This is the total number of lines passing through per unit area gives the electric field intensity, and remember, the lines must pass perpendicularly. For example, here like this, here like this, like this, here, now if you will put a particular area over here, for example here, now at present see the number of lines passing through this particular area, and if you will put the same area over here, then number of field lines which passes through this area decreases. Now here more number of lines are passing, it means the electric field intensity in this particular region is more and the electric field intensity in this particular region is less. So this is the area A, here this is the area A, and here more number of electric lines are passing perpendicularly. So the total number of lines passing through per unit area is called electric field intensity at that particular point, and the lines must pass perpendicularly. Fifth point, electric lines are not closed. It means these electric lines originates from the positive and ends at negative. It is not possible that electric line again comes from negative and ends at positive. No, they starts from positive and ends at negative. Therefore, electric lines are not closed. These are open lines. Sixth point, electric field lines does not crosses each other. They will not cross each other. See, this is the one electric line, this is another electric line. It is not possible that this is the one electric field line, this is another electric field line, they are crossing here. No. Reason? If they crosses, this is the intersection point. Here you will get this is one direction of the electric field. Again at this point, this is another direction of the electric field. So at the point P, you will have two different directions of electric field, which is not possible. Therefore, electric field lines does not crosses each other. Now we will study about electric dipole. As the name indicates, electric dipole means two different poles, positive or negative. Electric dipole means two different charges. Now, definition of electric dipole: a pair of two equal and opposite charges separated by a small distance. Two equal and opposite, the two charges having same magnitude but polarity is different. One is positive, another is negative, separated by a distance 2a. This forms a complete electric dipole. Now, the net charge of the electric dipole is 0 plus q, because both the charges are of same magnitude. So, plus q and minus q will be 0, but the electric field will never 0. The electric field lines will originate from the positive charge and ends at the negative charge, which you studied earlier. For example, NaCl. NaCl, sodium chloride, is the best example. That is, it has one positive charge and one negative charge. That is, the two ions are separated by a certain distance. The charge on the both ions are equal and opposite. Magnitude will be equal but having different polarity. After electric dipole, now we will study about electric dipole moment. What is electric dipole moment? Product of magnitude of either charge, any charge, because both the charges are equal, any charge and of the electric dipole and its dipole length. Here the dipole length is 2a. Therefore, the dipole moment is the product of either charge, any one, q into 2a. The 2a, the direction of the length is from always negative to positive. So, the dipole moment P, it is represented by P. Its direction is always from negative charge to positive charge. See here. Therefore, it is a vector quantity. Dipole moment is a vector quantity. Its direction is from negative charge to positive charge. And if you will find out the magnitude, then simple magnitude is P is equals to Q into 2A. Its unit is coulomb meter. Product of charge and the length, charge is having unit coulomb, length meter.